All right, ladies and gentlemen of bridge class. In the last video, we did a visual justification of the side-side-side triangle congruence theorem. And today we're going to use actually a picture from that right here to do a little bit more formal justification of side-side-side. And my objective is that you're going to use what you know about the definition of congruence in terms of rigid motions. Remember, rigid motions are translations, reflections, rotations, to justify the side-side-side triangle congruence theorem. And what we're also going to be doing here is we're going to be using our deductive reasoning. We're going to be reasoning from big picture principles that we accept and know for sure to specific conclusions. Here's the three principles that we have. Number one, or first one. If a figure maps exactly onto another figure through a series of rigid motions, translations, reflections, or rotations, we can say the two figures are congruent. This idea is very heavy in the New Common Core math, but it's in some ways very old. The famous mathematician Euclid from ancient Alexandria said that if figures coincide with one another, his words, or his words in Greek, meant coincide with another figure, then the two figures have to be congruent. So this is actually a rather ancient mathematical principle. We also have a definition. The kind of rigid motion we call a reflection is going to be a transformation where each point in a shape appears at equal distance across a given line, and that's called the line of reflection. So that's a kind of a technical definition of what reflection amounts to. And then finally, in a previous video, I taught you about the perpendicular bisector theorem. I'll mark this little bullet point here too. And the perpendicular bisector theorem, as you'll hopefully remember from the last video, just says that if a point is on the perpendicular bisector of a segment, then it is equidistant, the same distance from the endpoints of the segment. So those are the tools, the conceptual tools we're going to use to show that the two triangles we have here that we made yesterday, or I made this yesterday, that you saw in the previous video, are congruent. Those are triangles ABC and triangles ABD. So to do this, our goal is going to be to reason backwards from the concepts that I just talked about to show that a reflection across segment AB, use a different color here, this segment here, is going to map point D right here exactly onto point C, which would meet the definition of a reflection that we talked about before. So we're hopeful that we're going to be able to do that. All right, so the first thing along those lines is that you might want to notice that here, BC, I use a little bit different color there actually. Maybe this blue color. BC is congruent to BD. And if you don't believe me, go back and look at the video to how I made these triangles, and hopefully you'll be satisfied that the two lines are of equal length. The two line segments are of equal length. Okay, so if that's the case, I want you to look here at this perpendicular bisector theorem, which states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay, well, you might notice that C here and D here are equidistant from B, which means that if we drew a line segment, I'm going to do this in black, between C and D right here, then we could even say that point B, by the converse of the perpendicular bisector theorem, has to be on the perpendicular bisector of this line I just drew, the line segment CD. Similar logic on the other side. Okay, so I'll use still a different color. Notice, based on the construction we did yesterday, that line segment AC is congruent to line segment AD. Once again, by the converse of the perpendicular bisector theorem, we know that point A now, I'll use 2 check marks, is the same distance from point C and point D, which means that this line segment CD is going to be on the perpendicular bisector of or that point A is on the perpendicular bisector of CD, I should say. All right. Now, we know, I can make a kind of a bigger line here. We know that if we have 2 points, we can make a line between them. That's another just really basic principle of geometry that actually also goes all the way back to Euclid. So here's our line of reflection, or what we want to be our line of reflection. A, B. And now we're almost there. Okay, so let's go backwards. It says the definition of a rigid motion we call reflection is as follows. A transformation where each point in a shape appears at an equal distance across a given line, the line of reflection. Okay? Because AB is the perpendicular bisector of CD, then here's the center point. I'll mark it, I don't know, A, B, C, D, E. That point, or that segment DE is going to be the exact same length as segment CE, which means that if we were to fold the paper across line AB, that point D would land exactly onto point C, which is our goal. We've used logical reasoning to show that D is going to map exactly onto point C, which I'm hoping satisfies you, that since we have a perfect reflection and we believe in principle that if a figure maps exactly onto another figure through a series of rigid motions, translations, reflections, rotations, then we can say that the 2 figures are congruent, which is our goal. And I'm hoping that that again shows you that the the beautiful side triangle congruence theorem must be true. Have fun with it.